In this lesson, we're going to work a couple example problems with electric field, electric potential difference. So this is question 1 on page 496. It says, how much work is done by the electric field moving a negative 7.7 microcoulomb charge through a potential difference of 65 volts? Now, this problem is actually pretty straightforward if we just think about it in terms of the equation. We know that the work done divided by charge is equal to the opposite of the change in potential. This is the work done by the electric field on the charge as it moves through the field. So all I have to do is plug in what I know. And solve this equation for work, right? So work equals negative delta V times Q. Well, it moves it through a positive potential difference of 65 volts. So I'm going to use negative 65, the opposite of that, times this negative 7.7, and that says microcoulomb, so times 10 to the negative 6th. And when I do this, let's see, 65 times 7.7 second e negative 6. A negative times a negative is a positive. This gets 5.005 times 10 to the negative 4th joules. Okay, that's how much work is done by the electric field. Now, why is this positive? Let's think about this. Okay, so let's set up our electric field, and we have a positive plate. We'll put it over here, and we have our negative plate. We'll put it over here. Now, potential difference is in terms of positive charge. So this has a high potential. This has a low potential, but we're actually moving a negative charge to a higher potential. So if I put a negative charge here, which way is the force from the electric field on it? Well, the force from the electric field is this way, and it's going to move to a higher potential, which is this way. Well, since the force and the motion are in the same direction, it makes sense that that is positive work. Even though the electric field is this way, remember, electric field is the force that's is in the direction of a force that's on a positive charge. So the force that's on the negative charge is in the other direction. So it does make sense that this is positive work. The other example we're going to do is page 496. Again, this is question 11, which says a negative 6.5 microcoulomb charge at rest has 15 times 10 to the negative 4th joules of work on it by an external force. So a force from outside does work. It causes this charge to move through a field and gain 4.82 joules of kinetic energy. The question says, what's the potential difference between points A and B? Now, again, let's reason our way through this problem before I just start doing any calculations. Here's what I do know. I know that energy is conserved. So whatever energy I have to start with, plus whatever work is done, is equal to, so this is initial, is equal to the energy I have at the end. All right, that's the law of conservation of energy when we have work done. So if this thing is at rest at the beginning, it's got an initial kinetic energy of 0. Okay? It's got some potential energy where it started, potential energy at point A where it started, and then we have some work that's done to it. At the end, it's got some kinetic energy, so plus work. At the end, it's got some kinetic energy, and it actually tells us what that is. Its kinetic energy is no longer 0, and it has still some potential energy. So we actually can set this up, and then we'll draw the electric fields just to see how that works. And so, yeah, we can do it this way. So we're going to start with potential energy at A. We don't know what that is. Plus the kinetic energy at A. Well, it started at rest, so that's 0. Plus the work that was done on it. Well, the work that was done on it is 15 times 10 to the negative 4th joules. It says positive, so we'll go with positive. 15 times 10 to the negative 4th. This has to equal the kinetic energy it has at the end. Well, it says 4.82 times 10 to the negative 4th plus the potential energy it has at B. Well, this means all I have to do to find the potential difference between A and B, I'm going to do final minus initial. So PB, potential energy at B, minus potential energy at A. So I'm going to subtract this A to this side is going to be equal to this 15 times 10 to the negative 4th, and then I'll subtract that over, minus 4.82 times 10 to the negative fourth. So if we do this, 15 times 10 to the negative fourth minus 4.82 times 10 to the negative fourth, that gets me 0.001018. So the difference in potential energy is equal to 0.001018. This is joules. Now, the question didn't ask for the difference in potential energy. It said find the potential difference. Well, all I have to do to find the potential difference is divide this by Q. So potential difference is change in potential energy divided by Q. Well, the Q is negative 6.5 times 10 to the negative 6th. 6.5 times 10 to the negative 6th coulombs. And so divide 6.5 second e to the negative 6, and we get negative, the change in, that should be a delta, the change in potential is equal to 156.6 volts. Does it make sense that this is a positive change? Oh, it's not. It's a negative change. Does it make sense that this is a negative change? Well, let's think about what happened. Again, I'm going to draw my charge separation. I'm going to draw my uniform electric field. So here's a negative plate. Here's a positive plate. Now, an outside force did work on this thing and moved it through some distance. It gave it kinetic energy, but it did 15 times 10 to the negative 4 joules of work. This thing only gained 4.82 joules of kinetic energy. That means it had to be gaining potential energy. Well, which way do I have to push a negative charge so it gains potential energy? I have to push it this way towards the negative plate. So I have this negative charge, and then I do work on it, and I give it more potential energy over here. And so if this is position A and this is position B is at a lower potential, because remember, potential, not potential energy, but potential is defined for positive charge. So lower potential is at the negative plate, higher potential is at the positive plate. So it does make sense that pushing it from A to B, I moved it to a lower potential because I moved it closer to the negative plate.